I'm ready.
I want to start with high-speed aerodynamics. How do you interpret and validate a vendor's lateral critical speed map and stability analysis? Specifically, the log decrement for a high-pressure API 617 centrifugal compressor.
Well, the foundational premise here is that rotor dynamic validation is strictly about ensuring safe, continuous operation away from lateral critical speeds.
Okay.
Fundamentally, we must maintain a positive log decrement. That means a delta strictly greater than 0.1.
Right.
That threshold is absolutely required to prevent aerodynamic cross-coupling instability.
Let's pause right there because log decrement is a term that gets thrown around in engineering reports a lot. But I want to make sure we are grounded in the physical reality of what that number actually represents.
Sure.
For the sake of absolute clarity, what physically is happening when that number drops?
So think of log decrement exactly like the shock absorbers on your car. If you have a healthy positive number, say well over 0.1, it means when you hit a bump, the car bounces once, the shock absorber dampens the energy, and the chassis settles immediately.
Makes sense.
In a compressor, that bump is a microscopic perturbation in gas density or pressure. If your log decrement is close to 0, your shock absorbers are effectively blown.
Wow.
Yeah, you hit that microscopic bump, and the rotor just keeps bouncing. The vibration amplifies with every single revolution until the rotor deflects so far it actually hits the stationary casing.
That paints a very clear picture. So let's pressure test those exact margins. I need specifics here. When you are evaluating a flexible rotor operating above its first critical speed, what exact critical speed separation margins are you accepting from a vendor before you approve the architecture?
I do not rely on vendor preference. I strictly enforce API 617 requirements.
Okay, sure.
For flexible rotors operating above their first critical speed, the operational speed window must maintain a minimum separation margin of 20% above the first critical speed and 15% below the second critical speed.
I often see engineers treat those numbers like, administrative checkboxes. But they aren't, are they?
Not at all. Those API margins, the 20% above, 15% below, they aren't just arbitrary numbers some committee dreamed up.
Right.
They represent the exact physical threshold where the steel stops acting like a solid, rigid body and starts acting like a tuning fork.
A tuning fork.
Exactly. If you operate too close to a critical speed, the amplification factors during a run-up or during continuous operation will dynamically excite the rotor into a resonant condition. The shaft will literally bend.
Good. But let's apply some professional skepticism here, because this is where a lot of smart engineers get trapped. Let's say a vendor hands you a perfectly documented unbalanced response test.
Okay.
The vibration data looks incredibly smooth.
Okay.
But this test was performed in their vacuum shop. The rotor spun up beautifully, well past its operating speed with 0 vibration issues. Are you approving that machine for deployment to the field based on that data?
Absolutely not. That is a classic trap. And relying on it is engineering negligence. I would reject that approval immediately.
Defend that rejection. I mean, the rotor spun perfectly. Why is a flawless vacuum test insufficient for field approval?
Because a vacuum shop test cannot reveal aerodynamic cross-coupling instability. Verify a positive log decrement under full gas density to ensure rotor stability.
Because in a vacuum,
you have removed the gas entirely. Without gas, there are no aerodynamic forces acting at the impellers or leaking through the labyrinth seals.
meaning you are testing the mechanical balance of the steel, but entirely ignoring the fluid dynamics that will tear it apart in the field.
Exactly. When high-pressure gas flows through a labyrinth seal in the real world,
Yeah.
it doesn't just flow straight backward.
Right.
It acquires a tangential velocity. It actually spins in the same direction as the rotor.
Oh, wow.
Yeah, this spinning wall of dense gas creates a cross-coupling force. It pushes the rotor sideways, perpendicular to its deflection, which drives it into an unstable subsynchronous whirl. A vacuum test completely blinds you to that reality.
I appreciate that engineering intuition. It's essentially like testing an airplane's wings in a windless hangar.
That's a perfect analogy.
It might look structurally sound sitting on the landing gear, but it completely misses the real-world aerodynamic lifting forces that will actually act upon the airframe in flight. So taking that next logical step, you demand the stability analysis at full field gas density, and the calculation comes back with a log decrement below 0.1. The machine is mathematically unstable. How do you architecturally optimize it?
Well, if the log decrement is too low, I direct the vendor to immediately modify the machine architecture to introduce rigorous damping optimizations.
Where do you start?
We start at the ends of the shaft with the bearings, introducing tilt pad journal bearings with highly optimized clearances to break up oil whirl.
Okay, and then?
Moving inward to the gas path, we implement swirl brakes at the labyrinth seals. These are essentially stationary teeth that disrupt that tangential spinning velocity of the gas I mentioned earlier.
Right, breaking up that wall of gas.
Exactly. And if the instability still persists, we integrate a dedicated honeycomb or hole pattern damper seal at the balance piston.
Can you provide a quantitative field example where you actually had to intervene and force that level of architectural change?
Certainly. I recently reviewed an API 617 stability analysis for a high-pressure gas injection compressor intended for offshore deployment.
Okay.
The vendor submitted the analysis, and it returned a marginal log decrement of just 0.02.
zero point zero 0.02. That is perilously close to zero. I mean, going back to your car analogy, those shock absorbers are basically non-existent.
Exactly.
The rotor would have been highly susceptible to the slightest process perturbation.
It was completely unacceptable. I requested the immediate integration of a hole pattern balance piston seal.
And how did that fix it?
By replacing the standard smooth labyrinth seal with a hole pattern design, we fundamentally changed the friction profile.
I see.
The rough surface of the hole pattern creates massive acoustic and fluid friction, breaking up the tangential gas flow and dramatically increasing the effective damping at the balance piston.
Wow.
Yeah, that single change pulled the log decrement well above the 0.1 API threshold, securing the mechanical stability of the rotor.
That demonstrates solid architectural control. However, I want to address the operational reality once that machine is actually running in the plant. Process engineers love to tweak conditions to optimize yield.
Oh, they do, and that requires a very strict operational caution.
Which is?
Any field modification to process conditions that increases gas molecular weight or suction pressure will inherently raise the gas density inside that casing.
Right.
Higher gas density directly amplifies those tangential cross-coupling forces. That means the machine's log decrement will rapidly degrade, potentially causing severe subsynchronous vibration.
So it's not a set it and forget it situation.
No, the machine you mathematically validated on day one might not be the same machine dynamically if the process engineers alter the gas composition on day two.
Moving to another question, we've just seen how a shift in gas density can aerodynamically tear apart a high-speed centrifugal rotor. But what happens when we take that same unpredictable gas shift and apply it to a heavy-duty reciprocating machine?
That's a completely different beast.
Right, the aerodynamics might matter a bit less, but the brute force thermodynamics suddenly become the primary threat. How do you evaluate the thermodynamic and mechanical design limits of a heavy-duty API 618 reciprocating compressor operating under variable gas molecular weights?
Variable gas molecular weights fundamentally alter a triad of parameters in a reciprocating machine.
Which are?
The compression ratio, the discharge temperatures, and the combined rod loads. Evaluating this requires a highly rigorous, integrated verification of cylinder clearances, structural rod load limits, and valve selections.
Let's isolate the thermodynamics first. Assume the process demands a severe drop in gas molecular weight. Say we're switching from compressing a rich, heavy hydrocarbon gas to pure hydrogen. What is the immediate thermodynamic impact, and how exactly do you constrain it?
The immediate impact is a severe thermal spike at the discharge nozzle.
Okay.
To constrain this, I strictly enforce the API 618 cap, which mandates a maximum discharge temperature of 150 degrees Celsius or 300 degrees Fahrenheit for hazardous gases.
Let's break down the why for a moment. Why does hydrogen get so much hotter? The compressor is running at the same speed, pushing the same physical volume of gas.
It comes down to the heat capacity ratio, or the polytropic exponent of the gas. When you compress any gas, you are putting mechanical work into it, which generates heat.
Right, basic thermodynamics.
Exactly. A heavy, dense hydrocarbon gas has a complex molecular structure that acts like a thermal sponge. It absorbs that heat of compression relatively well.
And hydrogen.
Hydrogen is the lightest element in the universe. It has a drastically different heat capacity. It doesn't absorb and carry away the heat of compression effectively at all.
No.
The energy has nowhere to go but into the gas temperature and the surrounding metal, which violently spikes your discharge temperature.
And what is the mechanical reality behind that 150 degrees Celsius limit? Why is 150 degrees the absolute ceiling? Steel doesn't melt at 150 degrees.
Steel doesn't, but the non-metallic wear components absolutely do. Exceeding that temperature degrades the internal Teflon or PTFE piston rings and rider bands. Those bands are the only things keeping the steel piston from touching the steel cylinder wall.
So if they melt?
Once that Teflon melts or extrudes out of its groove due to extreme heat, you lose your sealing and you invite raw steel grinding against a steel cylinder liner at 1,000 cycles a minute.
That sounds catastrophic.
The machine will literally tear itself apart from friction before the operator can even hit the emergency stop.
Very well. Let's flip the scenario and test a mechanical trap.
All right.
Suppose our design pressure remains completely unchanged. The pressure gauges on the piping read exactly the same. But we switch the process to a significantly heavier gas mix. Can I assume the compressor frame can handle it, given that the absolute pressure hasn't exceeded the nameplate rating?
No, you absolutely cannot assume that. That is a critical structural trap that destroys compressor frames all the time.
Wait, hold on. Explain the physics of that to me, because on paper, the pressure is identical. If the discharge pressure gauge reads 1,000 psi on light gas and 1,000 psi on heavy gas, why would my frame suddenly snap?
Because the absolute pressure might be identical, but heavy gases significantly increase the differential pressure forces acting across the piston faces during the compression stroke.
Give me an analogy for that.
Think of it like trying to push a sheet of plywood through the air versus trying to push that exact same sheet of plywood through water at the exact same speed.
Oh, I see.
The water is denser, so it pushes back with massive resistance. When you compress a heavier gas, the gas inertia and density resist compression much more strongly.
So it's fighting the machine.
Exactly. This massive increase in differential force translates directly down the piston rod. It can severely overload the crosshead pin, the piston rod itself, and the entire frame structure. Variable gas weights shift thermodynamic and structural balances. Verify that rod loads and discharge temperatures remain within API 618 limits across all operating scenarios.
So it's not the final pressure itself. It's the sheer physical resistance of the gas pushing back against the piston to get to that pressure.
You've got it.
How do you practically verify that in an engineering environment before a gas switch is authorized?
Through rigorous computational validation. For example, when switching a machine from a hydrogen-rich stream to a much heavier hydrocarbon mix, I utilize specialized compressor simulation software.
And what's your benchmark?
My standard is to confirm that the frame's combined rod load, which includes both the gas load and the inertia load of the heavy moving parts, does not exceed 75% of its mechanical rating.
Why only 75%?
That 25% buffer is absolutely essential for absorbing transient process spikes.
And what about the localized components? The frame might hold under 75% load, but how do the valves react to that heavier gas?
Reciprocating compressor valves are essentially spring-loaded plates that open and close strictly based on differential pressure and gas density. If the molecular weight increases significantly from the design baseline, the gas has much higher inertia. The valves will struggle to pass this denser medium.
Meaning they don't open smoothly.
Right. They can experience severe fluttering, rapidly bouncing open and closed, or they close late, slamming violently against the metal seat as the piston reverses. This leads to rapid and repetitive valve plate cracking.
Excellent. Now, I want to pressure test the lower limits of this variable molecular weight scenario. We've discussed what happens when the gas gets too heavy, causing structural overload, or when it gets too hot from being too light. What is the operational caution when operating a reciprocating compressor below its minimum design gas molecular weight?
The caution here involves the fundamental lubrication mechanics of the running gear.
Okay, walk me through it.
If you operate below the minimum design gas molecular weight without utilizing automatic cylinder clearance pockets or variable volume pockets to artificially adjust the compression ratio, the cylinder pressure drops too low.
And when it drops too low?
When the pressure is too low, the gas does not push back against the piston with enough force during the expansion stroke.
And what does that lack of pushback mean for the structural integrity of the rod?
It means the piston rod ends up operating under continuous tension or continuous compression throughout the entire 360-degree crank cycle.
Which is bad, right?
Very bad. A heavy-duty reciprocating compressor relies on a momentary reversal of forces, a distinct physical shift from tension to compression at the crosshead pin.
Why is that reversal so critical?
Because that load reversal is the exact split-second moment the crosshead pin momentarily lifts off its internal bushing.
Oh, I see where this is going.
Yeah, when it lifts, it draws in a microscopic hydrodynamic wedge of lubricating oil. If you eliminate that load reversal because your gas is too light and isn't pushing back, the pin never lifts.
Then oil gets in.
Exactly. You eliminate the oil wedge entirely, you have metal on metal rubbing under thousands of pounds of force. This culminates in rapid crosshead pin seizure, which will instantly snap the rod and blow apart the cast iron crankcase.
Wow. Well, that concludes the technical assessment. You have successfully navigated the aerodynamic traps of API 617 and the thermodynamic boundaries of API 618, demonstrating a profound, uncompromising grasp of rotating engineering knowledge.
Thank you.
Listen, the days of flipping through static, outdated questionnaires, they are officially over. We're going to look at an entirely new ecosystem designed specifically for working professionals to help you master those high-pressure moments.
Okay, picture this. You're sitting right across the table from a panel of... They aren't asking about your hobbies anymore. They're dropping you directly into the hot seat to test your true operational readiness. Imagine you're in that interview. The pressure's on.
When you're facing intense, high-stakes scenarios in a real-world interview, you need something that prepares you for the absolute reality of the industry, where your split-second engineering decisions have massive financial and, of course, safety implications.
And that brings us to this absolutely game-changing app, which is available right now on the Play Store. What we're looking at here isn't just some random list of questions thrown together. No way. It is an exhaustively structured solution. It provides AI-driven, highly practical, example-based Q&As that form a comprehensive framework. Because the sheer scale of this architecture is massive. We're talking about a structure spanning over 200 sections, and it caters to everyone, beginners, intermediate folks, all the way up to experienced and expert professionals. The rule of thumb here is simple. If it's in the plant, it is in this app. It really acts as a complete pedagogical roadmap for your entire career. Now, you might be wondering, how does it deliver all this content without getting super repetitive? Well, the core of this app is what they call the Studio Engine. It's this AI powerhouse that entirely eliminates the limitation of predetermined static questions. Instead, it dynamically generates a highly structured, unlimited repository of practical Q&As right when you need them. So by doing this, it actually tailors a dynamic mock interview simulator specifically to your current knowledge gaps. It brilliantly illustrates how concepts are queued sequentially. You just select your domain, your section, and then your concept, and the app continuously feeds you the next logical scenario. Because getting a question is one thing. Understanding the multidimensional answer is a whole other ballgame. The system doesn't just feed you a wall of text. Every single generated response is deconstructed into 5 distinct steps. It actively highlights the critical responses you absolutely must deliver and warns you of the hidden pitfalls. Now, they represent only a minor part of the unlimited Q&As available in the app, but they serve a very specific, crucial purpose. They perfectly simulate real-world office arguments, differing viewpoints, and intense technical debates. Because let's face it, engineering isn't just taking a test in a vacuum, right? It's about navigating heated arguments and proving your technical acumen when challenged by your peers or your superiors.
And a massive part of these sessions is the power of roleplay. After every mock interview section, videos feature AI-generated live roleplay interview sessions complete with feedback on pertinent domain subjects. Giving real roleplay interviews after enriched technical discussions acts like an incredible catalyst. It is a tremendous confidence booster for any aspiring candidate, consolidating everything you've learned into practical, real-world readiness. Which leaves us with one final, very important thought. What step are you going to take right now to engineer your own success? Mastering your craft is a lifelong pursuit, and with tools like this at your fingertips, the depth of your knowledge truly has no limits. I highly encourage you to check out this combined integration of texts, text-to-speech audio, videos, and live role-play interview sessions. The tools are definitely out there to unlock your potential. The only question is, are you ready to use them?